So my name is Sanjay Sood. I am here from Momacmo. It's a small non-profit started just recently last year. Chuck Mosher, he is the founder. And our mission is to use geophysics for greater public good. And today what we are presenting is implementation of a technique for storing the data and using the data in cloud. So it is just built upon the work done previously using JavaSeis format for pre-stacked seismic data. And it has been used for the last 20 years by Halliburton Landmark's seismic processing system. So those who use SeisSpace, I think Alex Chevron does use that. They should be familiar with this. And others, I'll talk a little about that. My apologies to Alex and others who are using that. It may be some repetition of that. So outline, I'll not talk about, just touch upon what we know. So energy industry was the leader for HPC innovation and development for last so many decades. Things are changing, cloud is here, and so we do need to adapt, and I'll show our effort, a small, humble effort from a small nonprofit, how we can read and write data and use the capabilities of which cloud brings in to use it in our seismic processing. I'll show an example of a DAS data set, how we process it on the land, on cloud, using the open source Earth community implementation of Landmark's Halliburton SeisSpace in AWS Cloud. And also show an example of data science, small project on this data set done by a senior student at University of Calgary. So I'll not go into details about what all of you are the experts of this, and we know how to do it. The paradigm is the distributed synchronous parallel computing. So many people before me have talked about it. We just heard it in the last few talks also. But the things are changing. The cloud is not compatible with this mode of computation. So we need to rethink about how do we do computation, how do we store data, how do we use the native capabilities of the cloud to our advantage. So from the synchronous world or MPI, we need to move to some stateless kind of independent works which can be launched on some what in the cloud you call that serverless compute nodes, which launch, but with the launch of one instance, you can trigger something like that, but it has to be able to do that whatever you want to do it. So I'm showing an example, say, read the seismic data, filter it, do some basic processing, and write it out. So that is the kind of work which we do most of the time. But now it should be able to do it independently. We have to be able to read that. For that, you will need to provide infrastructure for starting, monitoring, completing these cloud tasks. And you will also need to assign, you should be able to have a key object storage, which is capable of this kind of input and output. So we'll show how we did it for this small project. So JavaSeis model of pre-stack seismic data. So it is very simple. So multidimensional data can be collected as collections of multiple 3D volumes, as shown here. And then basically in JavaSeis, you define a container, and you put your data into these containers. So say, for example, if you have a CDP gather, and then you will have that one volume CDP gather, it will be located somewhere in that container, and you have to define that container first, and as you read the data, that container will fill up. And what we are looking here, this is the live data. So this is the fold map of the data, and this is where your data is. The maximum bounds are defined by the bounding box. You cannot store the data outside those boundaries which you defined beforehand. So that is what is, you have to know what are the maximum extents of your data beforehand, then you can fill in those containers. So here is an example of a typical CDP gather type of data. So basically, just remember, so this is inline and crossline, and you have some fold. So maximum fold also you have to define beforehand in JavaSeis that, say, in this example, it is 30. So just remember two things here, because this will be, I will be talking about these in the next slide also. So volume and frame. These are some indices which we are using for defining the data. And once you know that, you can pinpoint and you can pull up a 2D frame out of this volume of the data set and look at the data. So for this example, there are 27 traces at volume location 5 and frame location 3. So that is what the data looks like. So this is objective way of putting the data. So this lends very well what we will be seeing in the next slide, how the cloud is storing its data. So what I'm talking about here is the JavaSeis cloud interface for AWS S3, whereas S3 is the simple storage service by Amazon. So we call this, in this you have a bucket. So a bucket could be, so that resides in a region in the cloud, so maybe in North America, Canada, or Europe, or anywhere. So, and then in that bucket, you can have then store those multiple volumes of your seismic data. And GSC S3 data set is mapped to a prefix in the bucket. So here is your bucket, and then this is a prefix. So this is a data set which is part of the prefix in the Amazon cloud. And then you can have that data set could have a hypercube, a volume. It could be, say, for a hypercube, say, it could be 5-dimensional data set, and then these are the, this is what it will look like. It will be a data set, hypercube, and volume. And then further the volume, there will be a 2D frame. Just so remember the previous slide, I talked about the volume and the frame. So these are the similar kind of things which are here. So there is a volume and there is a frame. Now, going further, so this is what your seismic traces, which we were looking in the previous slide, which are there for the JavaSeis. This is the same way. Amazon also stores this data set. So this is the seismic frame which can be pulled up. So if we look at it, so this is the bucket. So this thing is the bucket. And then this is the prefix, and this is the object. So the key for Amazon data storage in S3, so this is the key. So you need to know your bucket, and you need to know the key. Once you know that, you can provide to anybody or anywhere from any service, maybe from Amazon command line or from the browser, you can access that data set from anywhere. So this makes it available for, it lends very well that you can read the data, and then now you can use this capability to process the data. So here I'm showing, so we implemented this for our project on SeisSpace, which is the Halliburton's online SeisSpace Essentials. And we were able to read about the reading IO rates were around 10 Mbps. So the OEC implementation only provides one node. So there were 32 threads on that node, and it scaled horizontally to 320 Mbps for 32 jobs, which we were able to implement. And by launching the Lambda free tier, which can launch up to 1,000 concurrent jobs, we were able to scale horizontally up to 10 Gbps. And it cost us around $25 per terabyte to read and write. So that was the cost. So it is pretty cheap to read the data. Look at this. This is a workflow which works in SeisSpace, and this is we ran on cloud. And look at the first. So we are importing and directly reading from S3. So that's the Amazon cloud. And we are doing some processing. You look at, we are building some continuous records, doing some bandpass filtering, resampling, then bringing it back to the, say, channel domain and writing it out again back to S3. So there is no local disk required here in this example. So we were able to read the data, do some processing, and write it back to S3. So that's I think that is the beauty of this capability which we have we have been able to build. So this is just an example. So you are defining your region and where your data resides, and these are the extents, or this is defining where that key is. So that defines here. So for this example, so this is our giving us where the S3 is. This is the S3, and the regions are by default. So now I will talk about a small data set, not small for a small company like us. It was around 2 terabytes of data. This was a DAS data set. They acquired on using optical fiber cable way back in 2019, September, October. It was acquired on Mt Meager, active volcano, active in the geological sense. It had a large landslide, largest in the history of Canada in 2010. So they are looking at the geohazards associated. There are valleys and timber logging takes place in this, and there is a township down the river which flows down these mountains here. And so they are looking for that if there is a potential geohazard. And there is also interest in geothermal potential of under the volcano. So they laid a 3-kilometer long cable, and they acquired the data there. And we were lucky enough to get hold on to the data and do some interesting things with it. So at Momacmo, so for DAS processing, we looked at Amazon's use case example. So here they had a use case example in where they triggered Conagra, so tractor data. The data was going to the cloud, and once the data was there, it triggered an event, a Lambda function, and it was then going for a further processing. So we were able to adapt the similar kind of data, a similar kind of this routine or workflow for our case, and I'll talk about here. So this is what the data required was sitting on the servers of University of Calgary, Canada, and this was HDF5 data set. And we were able to use a simple AWS command line interface and copy the HDF data onto our S3. And once it was there, then Lambda function triggered, and that converted the data from this format, HDF5, to JavaSeis, and this is scale differential phase, which is proportional to the strains, which means, and we were able to, there were like 2,500 files. Each file was 0.8 GB, total data set 1.8 terabyte, and within 8 hours we were able to read. And the transformation and the read total took around 12 hours. So this is this format lends very well for any seismic processing. Now you have the data in a seismic processing kind of format. So here is, I'm showing you an example of, we used a noble technique to convert this time series data into the frequency domain. And you are seeing 10 windows of 10 hertz each from 0 to 100 hertz. And you see interesting things up to 50 hertz. So there are some seismic events here. You see some low frequency events, and then, I don't know, we don't understand what this is, so we call that noise. This could be signal maybe down the lane once we understand what this is. But at this moment, so there was nothing of seismic interest above 50 hertz. So the lower frequency signal was very interesting, 0 to 1 hertz signal. So looking at this, what you are looking on the vertical axis is the time. This is 1 day of data, low frequency, 0 to 1 hertz. And what you are looking at is these are the different channels. And if you look carefully, A to J are the channels in the valley, which are on the ground, and K to N are the channels which are on the ice. So we see a different behavior on ice and on land. So it's very quiet. So this day here is the UTC day. So this is 5 p.m. local time, and this is the 5 p.m. of next day. So somewhere here is the sunrise, and after you sunrise, we saw some interesting behavior with that, the change. There was some contraction or expansion of these with the sun coming up. Professor Rob Ferguson from University of Calgary, he looked at the data and he was able to plot the sunrise times, when was the sun hitting at those locations. And we saw a very interesting correlation between the sun time rise and the characteristics of the low frequency data. So that could be that it warms up and there is some expansion happening, and we don't fully understand what is going on, but this was an interesting observation which we saw in the low frequency data. There are some interesting features here up above here also, which we think are because of some cold wind blowing up the valleys from below, which happen during the night time. So that is what it is, we think. We are not sure, but this is our preliminary thinking. So then we looked at the 5 to 50 hertz frequency range, and we saw those winds blowing on some channels. So these are those valleys which we were seeing in the previous pictures also, low frequency also. And we saw when we blow up this portion of the data, so this is 2 seconds of data, and we see that there are some low frequency, some seismic events there. So these events are traveling at the velocity, shear velocity of ice in the ice portion and with the shear velocity in the rubble. So it looks like they are not coming from depth, but they are traveling across along the surface. So a lot of work needs to be done on this. So this is what we are thinking right now. And waveforms and the source mechanism analysis are underway. So we wanted to locate the event, so we did some interferometric studies. Energy density maps are shown here to locate the events, and this is a simulated event waveform, so which correlate very well to something, a rockfall happening down the valley here, and energy is reaching the cable here. So identifying events, so we looked at hour and a half of the data, we found around 64 events. But looking at the 30 days of data and finding out how many events are there was a very daunting task. So we thought of outsourcing it to the machine learning experts. So a senior student at University of Calgary was able to implement, so data was sitting in the cloud. He was able to use this cat and dog problem, very famous, very highly reliable algorithm available and does very well, which uses BGG16 deep learning network. And he was able to use that to identify. So we gave him an hour and a half data set of trained data set. There were 64 events in that. And then he was able to find around 900 events in 1 day of data. And this he used for his senior thesis. And he was able to publish this, I think in EAG, he has submitted a poster and in other formation. So what we mean here is once the data is in the cloud, it lends very well for any later machine learning kind of thing. So learning from the this Meager experiment. So multi-scale decomposition of the DAS data provides a wealth of domain to monitor physical processes. The low frequency of DAS response has intriguing correlation with the weather and temperature. So we saw numerous events, and deep learning networks were able to detect seismic events with good accuracy. And interferometric imaging has allowed us to locate events. These components could be used to create a real-time hazard detection system using DAS and the cloud platforms. To conclude about this JavaSeis, I'll just say that even though our industry has long been working with big data, we believe that there is much to learn from the success in the cloud computing world. In addition to shifting the traditional workloads to cloud, we believe that there is a significant opportunity to shift to this asynchronous, stateless type of capabilities which are available on the cloud, and we should look at these asynchronous style of computation. With that, I think I have run out of time. Thank you very much, and I appreciate your time.
Thanks, Sanjay. Last talk of the session. Any questions? Well, people ask.
I have a quick question. Are you doing anything else with other cloud providers like GCP or Azure Blob?
Yes, we are in talks with the Azure, with the Microsoft Cloud, and we will be implementing the very similar thing which we were able to do on Amazon with Microsoft. So we are in talks with them, and we will be very shortly be implementing this on the Azure Blob storage. Yes.
Hi. Did you pick up any telemetry data with regards to the amounts of puts and gets that were being leveraged by the framework? And if so, were there any surprises?
So this is not telemetry data. This was the data acquired in 2019. We got it last year, and we worked on it But if there is a good internet connection, we think this system would work. It is very simple. They already have implementation. From the agricultural field, tractor sensors are connected to the cloud. So that Conagra example, which I didn't talk about a lot, is actually very similar. That gave us an idea, how do we do that? So they are already doing it. With that, the sensor data is stored on the cloud. Once it reaches, a file reaches, it triggers a Lambda function, and it does the further analysis of the data. Yes, with the telemetry, it is possible. We have not done it. There will be some glitches, I can imagine, but it is possible to do that.
Let me just clarify the question. I may have asked it incorrectly. If we were looking at JavaSeis or SeisSpace on-premise, we'd have a significant amount of I/O that's associated with the file reads, whether it's a strided read, et cetera, multi-client access. Was there any indication from a object storage perspective with regards to reads or writes and what the impact could be?
No, so we were able to, so we just had the free tier for nonprofit. AWS provides this free tier Lambda function. We were able to concurrently run 1,000 Lambda functions. So that is basically 1,000 I/O operations. And we didn't see any. They scaled very well. It was a horizontal scaling. That is what we saw. So we went from 10 Mbps to 10 Gbps, from a single CPU to 1,000 CPUs. So there was no, we didn't see anything. But where the data is, where it is being stored, that could be. So we were talking about, when I'm talking about that Canada example, so data was sitting in Calgary, and our S3 location was also Canada 1. So that is what it was. It was not somewhere here in Houston or somewhere in the that way. So that is what we chose the location of our AWS very close to where our servers, local servers were.
Since there is a valuable follow-up to Tom's question, not knowing Tom and why he asked this question. Anyway, thanks. We're at the end of our session. Thank you again. Thanks to all the other speakers. Thanks to you in the audience for joining us.